Here we are. I think I hit the wrong Zoom link. Can everyone hear me? Hello? Everyone can hear me? Everyone can see me? Hello? Okay. All right. So welcome everyone. I'm going to open our Canva webpage where I just posted all the information. I'm going to share the screen with you in a sec. 3, 1, 2. Here we go. So let me share the screen with you guys. Here we go. All right. Now we start nuclear physics. So as you can see in the overview, there's some information of what we want to achieve. Information on the Zoom link. This will be the same Zoom link as we have for quantum mechanics. So I welcome everyone to the new lectures, to the new term, and we're going to start strong because we don't have much time. So basically today we're going to do a little bit of Burke properties of the nucleus, and here obviously in lessons you will have all the quantum mechanics, and underneath we have all the nuclear physics, right? So your Canva web page, and you have plots or figures which I attach here for you guys to have a visual interpretation of what I want you to remember. This is the binding energy curve. This is the nuclear shard, the landscape of nuclei. This is the nucleon potential or the nuclear force potential. These are decays, how the nucleus decays through beta, alpha, gamma radiation. These are neutron mergers, known to be nurseries of elements, of the heavy elements in our universe. This is the shell model, and this is the collective model. Some of the a collective motion of protons against neutrons. So all these are pictures that after this course we're going to understand better. So far we are going to go slowly, but we need to learn these concepts and this understanding of these figures in more detail. So in the introduction, I explain a little bit of what I want you to achieve, if not during this time, but achieve mostly for life. If you do science or you do physics, we need to build the concepts, not learning by absorption, by having an exam or by Googling, or you must do the work. The work requires that everyone takes a being like this and fill it up with paper, with scratch paper every day. That's your only chance to become a scientist, right? A physicist. You fill it up every day, and there's no doubt. You solve problems. You don't solve problems, but you try them until you solve them eventually. So I want us also to have a broad picture, a detailed picture of everything, of the nuclear physics, to be able to discuss, to be brave, and do not be afraid to express your ideas or ask questions. Always doubt. And it's always very important to know the weaknesses of the subject or the different concepts, and because if we don't doubt and we don't know the weaknesses, it's more difficult to make any discoveries, right? So the description, introductory description of the course. So we'll have basically we have a lecture which will come in these three forms: a PowerPoint presentation or a PDF, which I will upload into the Canva every day or every second day, a Zoom meeting. This Zoom meeting is to discuss concepts, questions. You have questions. This is the moment to do it. And through those questions and through those issues that you may find, I may prepare a special videos to overcome those issues. And for that, I need your participation. Obviously, there will be an assignment every week that has to be submitted. And I expect you to, as I say, to use your wastebasket, your bin, and fill it up with paper every day, doing calculations and trying to improve your mathematics skills, your concepts, and trying to understand physics, the graphs, So these are the two books that we're going to be, or one is a book, one is a preparation of a book. This is so far, let's call it lecture notes. This is my long-term project in making a nice book with fun concepts and issues in nuclear physics. And the first chapter will be nuclear properties, where we are going to revise the general properties and the nuclear landscape. What is our laboratory? And we are going to inspect what is the binding energy and the semi-empirical mass formula basically, we are going to apply Einstein's formula that you know very well to determine binding energies. And we are going to use quantum mechanics to determine the range of the nuclear force by using the uncertainty principle. And we are going to see also how to apply some classical physics to determine the size of the nucleus, some basic kinematics, and rather for scattering. So that's the beginning. And without any hesitation, let's just go in. And you see, this is the beginning of nuclear physics. Happens in a lab where you have this circular fluorescence screen where you could see flashes of light, and you have a little bit of a collimating alpha source here. It can be normally a heavy nucleus. A triple alpha source is composed of different nuclei which emit alpha particles, and those alpha particles are collimated towards this thin gold foil. And this experiment you probably have known already from modern physics in second year. And these particles, as you can see, most of them they go through, and most particles are undeflected, but few of them were seen at back angles. So that was kind of surprising, because before we have this plum pudding model of the nucleus. So in principle, the nucleus, it was all composed of electrons, and electrons couldn't stop these alpha particles. So it was unexpected that some of the particles were deflected and seeing at backward angles, right? So this obviously wasn't one of those experiments that we run nowadays with digital systems and gamma detectors, and we have this array called GAMCA, which means the lion, which is being commissioned right now for you to run experiments and do your breakthroughs. But this was a fluorescence screen where you could see only flashes of light. So these guys, actually Rutherford is always attributed as the discoverer of the nucleus, but these poor guys, Marsden and Geiger, were looking at these flashes for days and days and nights, right, to see whether this actually made sense, that these flashes at backward angles actually happen. Actually, they almost went blind, So the situation was that for this to happen, the atomic nucleus, the atom must have a nucleus which was at the center, and it was heavy enough to deflect these alpha particles. So not all the alpha particles will be deflected because the atom is huge compared to the nucleus. In comparison, you can see the head of a needle in the middle, in the center of a football pitch. That's the nucleus, and the football pitch is the atom with all the electrons going around. So that was the situation, and that was the beginning of nuclear physics. So then, after many years later, they discovered that the atom was made of nucleus. But then, by looking inside the nucleus, some discovered that there was some kind of current inside the neutron, which was supposed in 1932 the neutron was discovered, and the nucleus was compound of proton and neutrons, right? Which we call nowadays nucleons, both of them. And these proton and neutrons, obviously the proton is charged, but the neutron has no charge. So it was surprising to see that there was some little current inside the neutron. And this current inside the neutron, obviously, the overall current is 0 to make the neutron neutron. But this current itself speculated about the possibility of these quarks, having internal other more basic particles inside the neutron and the proton. So these were called quarks at that time. And you can see the scale, 10 to the minus 8, 10 to the minus 12 centimeters is the nucleus. So, 10 to the minus, what we call Fermis. Fermis is 10 to the minus 15 meters. And normally we use Fermi as the unit for nuclear physics, the same as we will use mega electron volts. And you can see the electron is much smaller, and the quark is also about the much smaller than the neutron or the proton. And you have here different degrees of freedom, where you have the quarks and the gluons. This is what we know. The gluons are we learn through time, the gluons are those, it's like the glue that keeps the proton and neutrons together, keep the quarks together, and keep them confined. So then we have the up and down quarks, and then if you go a little bit more to less energy, this is as a function of energy. You go to lower energy, you have the pion, which is the exchange force of the nuclear force. Basically, we'll go through that in a little bit. So we have pions, proton and neutrons. They're all baryons, proton and neutrons, and mesons. The pion, because the proton and neutron have 3 quarks and the pion has 2 quarks. So that's the difference between baryons for proton and neutrons and mesons, which is a pion. The pion is a meson, but there are other mesons, and things become more complicated. And then we go to the proton and neutrons composing the nucleus, and we have a vibrational state, decreasing the temperature. We go down in energy until we can look at the macroscopic properties of nuclei by using different models, which are very very useful. But it tells you here that there's more sensitivity, more resolution as you go higher in energy. We can see what is happening inside, and this is why we need these big accelerators to see what is happening inside the nucleus, and be able to determine the different bosons and mesons and all these particles, which are fundamental particles in the standard model. So one thing very interesting for you to see is that all this matter that we see around us, let me make this a little bit bigger so you can see it. All the matter that we see around us is only 4% of the matter, supposedly, of the matter in the universe. The 22% is supposed to be dark matter, which we don't know what it is. And 74% is supposed to be dark energy, which we don't know what it is either. So this is the summary. So this is our 4% of what we are alive, what we see around us, is the matter that we know. But astronomical observations, we need to see what's happening and why there are some stars which are far away from the galactic center, and they move as fast as those in the closer to the galactic center. It's like having Mercury and having Pluto. Pluto moves very slowly around the sun, but Mercury moves much faster, right? So what happened is here that we see that some stars in the halo of galaxies, they move very fast compared to the matter which is around, and that's why we infer this 22% of dark matter. And this is about the expansion of the universe. For the universe to expand, we also need more dark energy. Otherwise, with the current matter, the universe couldn't be expanding as it is right now. So these are things that are strange to us, but this is what the current understanding, and I say current because this may change anytime, but basically the normal matter, everything around us, you, the computer, the screens, the walls, the mountains, the people, everything is just 4% of all matter in our universe. So this is just giving us a broad picture of things. So here we have the typical nuclear landscape. This is called the chart of nuclei, the nuclear chart, right? And here we see, let me actually make it a little bit bigger from this, no, from this one, no, I want this one. All right. So here we have what I call the nuclear chart, and you have all kinds of nuclei being discovered in kind of a snake skin, right? This looks like the skin of a snake, but it actually represents all the known nuclei, which are about 3,000 known atomic nuclei. Out of those, 270 are stable and are represented by these black squares here. And then we have some unstable nuclei. And these unstable nuclei, because they have an extra proton, they decay by a beta plus, which is basically a proton is converted, as we discussed in the sodium iodine Prague. A proton is converted into a neutron plus a positron plus an antineutrino, plus a neutrino actually. And in this case, these guys here on the right side of this line of stability, which is the red squares, as I say, these guys are decaying by beta minus, which is basically a proton is converted into, actually a neutron is converted into a proton, a plus an electron plus an antineutrino, right? This is the typical beta decay. And this, as I mentioned during the Pragues, every guy here, every unstable nucleus wants to eventually become a stable nucleus, and it decays by either alpha, beta, or gamma radiation, right? So all these guys eventually they come down to the black squares. So there are many things we have to learn here, and there are these lines set equal 50, which means proton number equal 50. That represents a special magic number, and we'll go through those later on. These are part of the nuclear shell model, which is one of the chapters. And you see, this is another magic number which goes all the way here. This is 82, and these magic numbers, they have particular nuclei here which are more stable than others. It's basically the same as with atomic physics, where the noble gases, helium, neon, xenon, argon, they have particularly stable properties. And in nuclei, we took, and we'll see this later, we took the same idea from atomic physics, but without much of an understanding of the situation. We just stole the idea, and things work somehow, and we'll know why later on through the different lectures. What are the limits of this nuclei? When a nucleus becomes unbound, just before you can bind a nucleus it just gets basically it becomes particle unbound. Just basically you cannot form that nucleus in particular because there's not enough energy to bind the nucleus. So this was the line of stability, as I mentioned before, the black squares, and these are the known nuclei in green here. But it is supposed to be a lot more nuclei going. All this white stuff here is like a terra incognita. We haven't discovered any of them, and there are many millions and billions involved in this in discovering this terra incognita of nuclei. About 4,000 of these nuclei remain unknown, and these are the borders of stability, right? These are called the drip lines. A nuclei can be produced up to reaching these borders, which are not well defined, as you can say. It's not like one unique border, but there's a lot of uncertainties, and we are working on these uncertainties and see whether we can narrow down this possibility. I mean, this creation of elements. How are they created? And this is what we are also studying, because we don't know why. There's a certain property which tells us that the abundance of elements in our universe is quite a universal property. So if elements, as you know, and we went through this in the first prac, sodium prac, the elements are created in stellar explosions, and these energies are enough to produce lots of neutrons. All these heavy elements have produced lots of neutrons going this way, and eventually the competition between beta and beta decay and neutron capture. Every time a nucleus captures one neutron, these stellar explosions of neutron star mergers, for instance, two stars merge, and you produce lots of neutrons, and you go all the way here up to the point where the nucleus becomes unbound. Beta decay is favored over this process, and these are all the different reactions that may happen and all the different paths that may produce elements, right? So they are called, through stellar fusion. Here we have the RP process with the rapid proton process. There are lots of protons being involved, and you can capture them. The R process is the rapid neutron capture process. The P process is the proton process. Neutron stars process is supernova cores. S process is slow neutron process. So there are many network pathways which produce the elements as we see them today around us. This is, as I say, I'm giving you a global picture of what is happening. But one thing, as I mentioned before, these are unknown nuclei, and this prediction of the borders of nuclei, of the existence of nuclei, is not very well known. It's very important for us to understand how what are the limits of nuclear production. It is also important for us to understand the elements around us and how they are produced. For instance, how the building blocks of life are produced. And in this particular case, as I mentioned before, we have fusion, and through fusion you have an alpha particle. I mentioned also in the pracs that the protons in our sun, they combine with other protons, and they fuse, and they produce something heavier. Then that something heavier capture another proton. Eventually, this is the fuel of our sun, and that's how energy is produced through Einstein's equation of energy is equal mass c squared, speed of light squared, where mass is basically delta mass, which is the mass after and the mass before, and then you always have a production of energy up to reaching the iron nuclei, and I will see this in the binding energy curve, which we'll go through tomorrow or the day after. And then through these nuclear reactions, now let's say that we have we have finished with the hydrogen, and we converted eventually hydrogen into helium, and that helium is an alpha particle, as you can see here. It's 2 protons and 2 neutrons that they combine if you have enough temperatures, and through tunneling, quantum tunneling, you fuse them into beryllium-8, but beryllium-8 is unstable. But if, and this is a big if, a very, very almost miraculous if, there's energy. Actually, if you have an alpha particle coming with the beryllium-8, you can combine them and produce carbon-12, because beryllium-8 is 4 protons and 4 neutrons. Alpha is 2 protons and 2 neutrons. So you combine these two, you get carbon-12, which is 12 is the mass number, which is 6 protons and 6 neutrons. So in this case, we can always let me go back. You know, whenever I want to explain you something, we'll use something. You can ask me any questions where you need me to explain things in a little bit detail. So let me see at the chat. There's any questions so far? Guys, you can ask, you can talk and interrupt anytime. So I assume everything is okay, but I just wanted to tell you that when we talk about the carbon-12, this means that we have 6 proton and 6 neutrons here. Oh, let me see. Let me get this closer to me. Right. So normally this is A, which we call the mass number. This is Z, which is the proton number, and this is equal to N, which is the neutron number. So A is equal to M plus Z. Okay. So this is how we are going to label different nuclei. So we say the alpha particle is equal to 4 helium, which has 2 protons and 2 neutrons, right? So I'm going to leave this open. Questions? You know, there's a lot of things in this presentation. I'm doing an overall subject, but any of these slides will take years to explain properly. And there are years of work just done, for instance, on this slide right here. Right. So there's a nice. This comes from Physics World, and it's a nice article, which I also show it to you for you to learn. But what I was going to tell you is the following. You know, the energy release through Einstein's equation to combine this alpha, and let's make this bigger, to combine this alpha and this beryllium onto carbon-12, there's an energy release. But the energy release, or the time of producing this, will be very, very slow to produce any carbon in our universe, very little carbon for anyone to be alive. And this is what I meant to say before, that it is almost a miracle that the energy release of these two, through applying Einstein's formula and getting the masses of these two guys before and after, this energy release equals an existing state in carbon-12, about 7.654 MeV, 7.654 MeV, which has a kind of a magic number. And it's a magic, really a magic state, because without it, we won't have a resonance, the resonance that we need to produce enough carbon and to produce life, right? So this resonance allows for the process to be a much faster process, and allows for the production of helium of carbon, sorry, as we see in our universe. This is called the Hoyle state. It was Hoyle who predicted it in a way, because it was the only way for us to understand there must be a state like that, otherwise we wouldn't be alive. This is a principle, a philosophical principle, that sometimes something must be there, or otherwise it's not. There's no reason for us to be alive. So then we go and try to discover this state, and this is how at Caltech, the California Institute of Technology, this state was discovered after Hoyle predicted it. So whenever we see something happening, there's always we always have to wonder why this is happening, and if it happens, there must be a reason behind. Questions? Let me stop a little bit here. I'm going to stop, not stop sharing, but I want to see what's happening in the chat. Here we go. So I don't see any questions. As I mentioned before, we need to ask questions, because this is your time to learn concepts. So let me keep going, and let's go through it quickly, and then I give you time at the end to ask some questions. So this is, again, one of those big discoveries. So it was for the first time, there were calculations done from first principles where you could solve, like the problem of, this is a very complicated problem, as we're going to see in a little bit. So there was a huge theoretical attempt to predict the properties, or to calculate the properties of the Hoyle state, and it was done recently in 2011, only 10 years ago. And this was one of those theoretical achievements done in the recent years. And let's go a little bit to the problems. We have lots of problems with the nuclear force. Nuclear force, or the strong force, is not a force which is as easily tamed, as the gravitational force, in the sense that it doesn't have a nucleon or a nuclear potential. There's not a specific formula, a specific equation, like for the Coulomb force. You know what is the Coulomb potential, right? Or you know what is the gravitational potential. But for the nuclear force, is more difficult. And no one has so far come with a final solution to this issue. This was said in 1953 by one of the fathers of nuclear physics and nuclear astrophysics, that more man hours have been given to this problem, or trying to understand the nuclear force, than to any other scientific question in the history of mankind. This remains true nowadays. This is the problem with the nuclear force. Sometimes we call it nuclear force, and sometimes we call it nucleon-nucleon interaction. Basically, the interaction between two nucleons, one proton, one neutron, one neutron, one neutron, one proton, one neutron, any combination of nucleon-nucleon interaction. So this led to the point to say there are a few problems a little bit later, in 1950 and 60. There are a few problems in modern theoretical physics which have attracted more attention than that of trying to determine the fundamental interaction between two nucleons. It is also true that scarcely ever has the world of physics owed so little to so many. This guy, Goldberger, he was at Princeton, a professor at Princeton, director of Caltech. So he was a big shot. I wasn't very happy with the situation of our understanding of the nuclear force, as you can see. But expressed quite roughly, but the problem of the nuclear force is the nuclear many-body problem. What happened with the nuclear force is that we are dealing with a system of particles whose number is neither small enough to allow direct solution through, say, the Schrödinger equation, or nor large enough to make statistical methods highly accurate. We have a nucleus with 12 particles, right? So this is not a number where you can actually apply statistical mechanics, and which interact, as I say, through an interaction that has still not been pinned down to any definite form. It was in 1996, and there's a nice book which I use, but it's more advanced than Crane. But it's also a very interesting book. So if you want to, these books are in the library as well. What is the problem actually with nuclear physics? You know, it says that neither to allow direct solution nor large enough to make statistical methods highly accurate. The problem is this coupling constant. Every force has a coupling constant, which tells you how strong or how weak the force is, and allows for a quantum description, which here I call it perturbation plus renormalization. But this is a powerful mathematical framework to calculate properties of, you know, of the weak interaction of the Newton, of gravitation, electromagnetic properties. So here we see that the coupling constant for electromagnetism is 1/137. The coupling constant for the nuclear force is about 1. And we have for the weak force 10 to the minus 6, 10 to the minus 7. For Newton force, we have the gravitational force, we have 10 to the minus 39. So you have a small coupling constant, then you can do this power expansion, this perturbation plus renormalization techniques. But unfortunately, in our case, you cannot do it without paying for it. So this is the case of nuclear physics, and this is why this is so difficult. This many-body problem, the coupling strength, you know, the fact that we don't know the potential, it makes nuclear physics so far the most difficult problem in science, even nowadays. So this approach of perturbation approach was very effective in something called the quantum electrodynamics, where it merged electromagnetism and the weak interaction, that interaction for beta decay, and explain things to 1 part in 10 to the 8. So this approach of perturbation theory and renormalization was very successful in the 60s, 70s, and there were Nobel Prize winners given to this quantum electrodynamics, and that's why it took actually over our understanding of any physics. Everyone wanted to apply this perturbation plus renormalization techniques, including in nuclear physics, but in nuclear physics, what we would call high energy physics. As you go in high energy physics, and this is GeV, is 1,000 of MeVs. So obviously, as you increase the energy, the coupling constant for the nuclear force decreases. So we have for 1, which is up there, for 1 is our realm of the nuclear physics that we see in stellar explosions or in nuclear reactors. But the physics of very, very high energies has something called asymptotic freedom. Basically, as you increase the energy, and that's why you need very big accelerators for these things to happen. You have the confined quarks suddenly, as they get close to each other, as you increase the energy, the quarks also get close to each other, but basically they have another degree of freedom, because now they are not tied by this force, by the strong force, but now they are asymptotically free at short distance, at very high energies, as I say. So this again is crucial for us to apply quantum mechanics and be able to calculate things at these very, very, very high bombarding energies. This is the approach that we have nowadays. As I mentioned before, this quantum electrodynamics, these are Feynman diagrams. And this is basically what is happening. You have the exchange of a particle which describes the force. So forces appear because of one matter particle emits a force particle. So these exchange particles are carriers of the force. And for instance, we have photons, pions, omega W bosons, or gluons as part of these exchange particles between electrons. We have electrons interact with each other, or protons interact with each other through the electromagnetic force, and then there's always a virtual photon which is being emitted. And then we have the weak force. Neutron decays into a proton plus an electron plus an antineutrino. There's an exchange which is called the the W boson. And there's a strong force, where this is also called the color force for these high energies, where we can again apply quantum, what is called quantum chromodynamics and perturbation theory and renormalization techniques. And between nucleons, there's an exchange particle called the pion, but there are many pions, other mesons being involved, the pi meson, I mean the psi meson. There are many mesons involved in this exchange between proton and neutrons. In this case, but it could be proton-proton, neutron-neutron, as I say. This is before scattering, and this is after, and the exchange particle is here, and represent the same thing as these two guys on top of a boat, right? You exchange the particle, and your boat recoils, and you also recoil, and that's a kind of an illustration of this picture, which is a dominant picture in our physics nowadays. So obviously these are different Feynman diagrams, and it's a little bit more complicated than that, than just these four that we see here. There are more perturbative methods, and we can apply this is leading order, next to leading order, next to next leading order, next to next to next leading order perturbation. So this is called something chiral perturbation theory, but just an example of different Feynman diagrams which can explain, for instance, 2 nucleon forces, 3 nucleon forces, 4 nucleon forces, and so on and so forth. For this to happen, we need supercomputers. We need supercomputers to solve this, the physics, the quantum mechanics, the Schrödinger equation. You know, we need to solve a huge matrices and to determine the energies of the states. You know, solving Hamiltonian times the wave function equal the energy wave function, and then we need very much increasing calculating power, computational power, and this is what is happening nowadays. I don't want to go through any of these methods, but basically this is the Jaguar supercomputer in Oak Ridge National Laboratory in the US, which has 54, we can do actually 54 trillion mathematical calculations per second. It has over 200,000 microprocessors. You can Google it. It was the second of the time, at the time, the second fastest computer, or the biggest computer. So over 200,000 microprocessors. You know, this is what you need to do these kind of calculations. Very, very demanding. But I want to leave it here. There's we cannot rely on computers. They are important and we must learn, and that's why we are doing all these mini schools and these colloquiums and these workshops and these online pracs for you to learn computers and to learn how to program. But we cannot rely on computers, because I think, you know, we cannot rely, the discovery cannot be linked to a better computer, right? We must be smart enough to try to think about ways to make things happen, and to, you know, to go deep into the subject and make our own discoveries, look at the data, and be able to do things that you know, a computer is good, is great, but we cannot just wait for the best computer, quantum computers, to happen for us to make the next breakthrough, right? So this is my take for lecture number 1. I give you an introduction, a short but very deep introduction. This is very dense also, because each of these slides has years of discoveries, you know. So it's not easy to, but it gives you an overview, and then you can go to these papers, you know, you can see what are these different art process, you know, you can go and have a broader picture yourself Just Google this, go to the library, get a couple of astrophysics books, or nuclear astrophysics, get the Crane, or get any books you like. We need to learn. We cannot think about the always, we need to pass, we need to do this, we need to get the marks. The only thing you need to think about is about learning and enjoying what you do. Okay, here I'm going to stop sharing, or I have lots of questions now. Yeah, see? Yeah, how do they hold the game process is my question. I think how did they create the helium alpha particle? Okay, that's a very good point. So let me see. Okay, so that's a good point. So as I mentioned the other day in the prac, there was something called in our SAM. Our SAM does the proton chain reaction. Okay, and with this it produces energy, the energy that we see around us. And here you can see exactly how energy is produced. So we have a hydrogen, a proton, basically. Hydrogen, as I say, A is one proton and 0 neutrons. This is a proton, which is labeled as hydrogen 1, and another hydrogen, and these two hydrogen combine, and there's an emission of a neutrino, this new particle here. It's a elusive particle, and so we have, then we produce the deuteron, which is 1 proton and 1 neutron. Then the deuteron get another proton, and there's an emission of a gamma ray, and here we see the production of helium-3. The same thing happened on this side. So there's another 2 particles, 2 protons, but they combine with each other and emit a neutrino, and here's a positron. And then again, the same process happened. There's deuteron here, and there's another hydrogen coming through, which they also fuse together through, because we have enough temperatures for these guys to go through and fuse, and they produce helium-3. Also, quantum tunneling is very important for this process. And once you have these 2 helium-3 alpha particles, which is 2 protons and 1 neutron, then there's another, they combine, and they, in the combination, in the fusion, you expel, you get rid of one proton each, leading to the alpha particle. This is the process that it happens in our sun right now. So our sun is emitting, is doing the PP chain, right? The PP chain, and is converting basically hydrogen 1. Eventually, all the hydrogen ones, they convert into helium-4, right? So this is our sun right now. After 5 billion years, the hydrogen will we will have more fuel, more hydrogen fuel to keep burning and emitting radiation and heat to our Earth here. So this will be the process. So then what will happen is that the sun itself will reduce in shape, similar to PNRT. So to PV-NRT. So as you increase the pressure, you increase also the temperature. So this will reduce in size at the beginning, because there's always a competition between gravitation, which pulls things down, and the electromagnetic force, or which arises from the nuclear reactions, which brings energy out, right? So this different PP chain brings energy out from the center of the sun, and that's why we have these constant emissions, and these flares of the sun going out But however, once there's no more protons in our sun, there's no more fusion for a time, and then gravitation wins, and then the sun is reduced in size. But that reduction in size implies that we increase the pressure, and so we increase also the temperature. Eventually, whatever was helium-4, we also again fuse with helium-4, and our sun will become much bigger because the energy is much more than what we have before for the PP chain. And we better escape at that time with one of those, how is this South African guy called? Hopefully he makes his rockets for us. Elon, the Elon guy, hopefully we can take some of his rockets and go somewhere else, a little bit farther, maybe Mars or something, you know, for us to keep living in a different planet.